Welcome to learning module number 3, crystal and amorphous structure in materials. In the previous module, we looked at how atoms bond with each other and how the type of the bond determines the material's properties. Today, we will be expanding the picture, meaning that we will look at the entire crystal structure of materials. Now, materials can be classified into crystalline, amorphous, and semi-crystalline. Let's look at each other one by one. Now, crystalline materials are the ones that possess long range order, and that is the key here. And hopefully you recall that I did mention that before when I was describing metals, because metals are crystalline materials, meaning that they have a long range order. Okay, now amorphous materials are the ones that we also call disordered. An example of the amorphous material would be polymer. And earlier I did describe polymers as a bowl of noodles where you see these entangled, disordered chains, right? Something to keep in mind is that amorphous materials may possess a short range order. Okay, and now semi-crystalline. Semi-crystalline materials, the best way to describe them is that they are amorphous, but at the same time as you inspect the material, you may see some ordered regions within the amorphous material, and this is why we call it a semi-crystalline, because in a sense it possesses both. Now, something that we've already known before is that the properties of materials are influenced by the bonding force between the atoms. And what is new for us today is that the properties of materials, they are also influenced by the crystal structure. Typically, if we ought to represent the crystal structure, we usually refer to a space lattice. And by definition, space lattice is the infinite 3D array of points or lattice points. And this is exactly what you see depicted at the bottom right corner. All of those points, or perhaps spheres, this is an approximation of an atom. Now, luckily, whenever we describe a space lattice, we don't need to describe the entire infinite 3D array. We can actually look just at the unit cell. And the unit cell, it is the smallest subdivision of the lattice. And the main point here is that the unit cell maintains the characteristics of the overall crystal. And here's an example of such. So right in here, you're looking at the space lattice that was shown on the previous slide. And if we ought to take the smallest subdivision that maintains the characteristics of the overall crystals, you will be looking right here, picture B, which is your unit cell. Now, units or unit cells are extremely small. And I will give you an example. If we are to take the unit cells of iron and we're gonna line them up side by side in 1 millimeter, so hopefully people can imagine how small that size is, right? Then within that length, right, within that 1 millimeter, you will actually have almost 3.5 million of unit cells. Okay, so what we need to know about the unit cells in terms of characteristics is that they are usually defined by the axial lengths, and that is going to be A, B, and C. And allow me to demonstrate it here. So this is going to be your length A, this is your length B, and this is your length C. And in addition to that, unit cells are also defined by the interaxial angles, which is alpha, beta, and gamma. And right in here, I'm showing you this is going to be your angle alpha, beta, and gamma. Okay. Now, to characterize all existing crystal systems, you only need to be familiar with 7 different types of unit cells. And they're all depicted in this figure in front of us. Now, those include, and allow me to zoom in. So those 7 actually include cubic, right? And these are the three in the column number one. Then tetragonal, which are depicted right here, orthorhombic, which are right here, the entire column, right? Rhombohedral, hexagonal, monoclinic, and triclinic. Okay, and so all of those will be characterized by the uh, to define those, all you need to know are axial lengths and interaxial angles, right? And so hopefully all of these shapes are familiar to you. We won't be diving into all, and to be honest, it is entirely unnecessary. Within this course, you will learn quite a bit about cubic. And the reason we're not going to be diving into more, because if you are familiar with cubic, it is very easy, if you ever have to do it, it is very easy to expand your knowledge and build on top of cubic because the concepts, they remain almost the same, okay? Now, since within this course, we're primarily interested in metals, right? And most elemental metals, actually about 90%, crystallize into three densely packed crystal structures. And those include, two of those will be cubic, body-centered cubic, face-centered cubic, and hexagonal close-packed. Now, something to before I dive into each independently, I would like to remind you that whenever we look at the crystallization, right, and I want you to visualize it. So to actually observe the crystallization process of the metal, you first need to liquefy it, right? Meaning that you need to melt it. You need to heat it up. Once it liquefies, right, it's very, very hot. Then we're going to remove the temperature. Once you remove the temperature, obviously the material will begin crystallizing, right? Now, something to keep in mind is that during crystallization, energy is released. Why? Well, because the atoms come closer together and they bond tightly with each other. And we already know that when we were looking into the bonding, right? Because one of the slides did tell us that the driving force for bonding between atoms is lowering the potential energy of each of the bonded atoms, right? And this is why the energy is actually released. All right, now let's look at each. Body-centered and face-centered are cubic, and they will be the focus of today's video. I won't go deep into hexagonal close-packed, but I will show you optional slides for those who are interested to look more. Now, since body-centered and face-centered are both cubic, I do want you to actually visualize a cube first, because the difference is the following. For the body-centered, you will, of course, you will have a cube, and in the corner of each, in each corner, you will have an atom, right? And that's the portion that refers to the cubic portion. Now, body-centered, that means that at the center of the cube, you will have another atom, right? That's body-centered. Now, face-centered, very simple. You, again, start with atom in each corner of your cube, and then you have an additional atom in the center of each face, right? So that means if I am to take, let's say, this center, that means I have to put it right here, right here, right there, right there, right there, and right there. And that is the difference, okay? Now let's look at each, and I do have better visualizations for you to facilitate the process for you to familiarize yourself with these cubic cells, right? Now, body-centered cubic cell, and we often call it as we shorten it to BCC. A few things to keep in mind is that the axial lengths are equal. A is equal to B equal to C, perfect cube, right? All of the angles, alpha, beta, and gamma, are equal to 90 degrees. Now, it says that within the cell, within the BCC cell, you have two atoms. And I want you to actually understand where that comes from, right? And how do I calculate that? Okay, I think perhaps this is the best representation to help you understand why we say that there are two atoms, right? Or in a sense, the space that is occupied by atoms within the unit cell is equivalent to two atoms? Well, of course, I have this one guy right here. That's your one, right? Plus. And now I want you to envision what is actually in each corner, right? Because you're taking into consideration just the cube itself. I would like you to envision an onion, a tomato, or an apple, right? Something spheric. And I want you to now chop it, right, twice. And basically you will be, as you open it up, you will have 8 separate pieces. And that's exactly what you have in each corner, right? And this is why we have 1/8 8 times. And that's how we end up with two atoms. Now, for BCC, each atom has 8 neighbors, right? And it's kind of easy to calculate, right? If you, let's say, for visualization purposes, take the atom that is inside, right, in the center, like this guy right here in the core, right? This is going to be your one atom. And if you ought to envision the neighbors, you have 4 on top and then you have 4 on the bottom, which will gives you 8 neighbors overall. And this is why we always say coordination number is 8. Okay. Now, examples of such metals include chromium, iron. Iron is tricky. Later on, iron is tricky. At some point, it can change the crystal structure a little bit and then go back to the original one. I will show you this phenomena in detail at the end of this lecture, okay? But typically, up to very, very high temperatures, and especially at room temperature, iron is a BCC, body-centered cubic material, right? Tungsten, right? Tungsten has the highest melting point, right? And tantalum. These are just the examples. Okay, what else should we know about the BCC cell? Well, we need to be able to do a little bit of math. And right away, I see that there is a mistake. So allow me to do the following. This square root should not extend beyond the 3. It's supposed to be square root of 3 times A, right? For every single crystal structure that you will be familiar with, right? And that is going to be BCC, body-centered, and face-centered. I want you to know the relationship between the unit cell length, A, right? This is an example, right? This is your side A, and the radius of the atoms, right, that compose the cell. Now, the relationship is already given to you right here, right? And that is the square root of 3 times the length A, and it's equal to 4 times the radius, okay? This is the radius. Why don't we understand where it comes from? Because it is extremely easy, okay? Well, this 4 times radius comes from, this is just this line, right? Because if you guys think about it, it crosses 3 atoms, right? You have a radius here, you have 2 radius here, and a radius here, and that's how you end up, if you sum them all up, you end up with 4. And it says that the same length will also be equal to the square root of 3 times A. Okay, how do we come up with this one? Well, to help you understand, I'm going to draw this line first, and I want to find out what that line is. And the answer is already here, right? It's square root of 2 times A, but I want you to understand where it comes from. Look at this triangle right there. And let me remind you the Pythagorean theorem, right? Where we know that a squared plus b squared is equal to c squared, and the c is actually the longest side, right? And that's going to be exactly the blue line that I'm looking at. So if this is a, and if this is a, I know that that side is going to be a squared plus a squared is equal to whatever is there, but since I 2a squared, right? That's the squared answer. So in here, it's going to be square root of 2 times a. right? That's how we arrived to this. But now, let me highlight the next circle where I should look at. Now, sorry, the next triangle, right? Now I'm gonna look at here because that's how I'm gonna connect my radius uh, to the unit length, right? So I'm gonna keep my color purple. I'm now looking at the purple shaded triangle and I'm trying to apply the same Pythagorean um, um, theorem, right? And it's going to be 4 times radius is equal to what? 2a squared plus a squared. And it's the same as 3a squared. And that's how I end up with exact same, or perhaps I flip the sides, right? But from here, that's exactly the same thing, right? Oh, well, I rushed a little bit. I forgot to apply the square root, right? I forgot to apply the square root, and then it's going to be like this, right? Because the 4 radius, it's already the square root has been applied. Okay, so hopefully that makes sense, relatively easy. How do I apply it to a specific problem? Well, let's look at the example problem right here. Uh, Estimate axial length A for a BCC iron with an atomic radius, and the radius is given. Well, first thing I need to identify is the crystal structure, right? Or perhaps the crystal structure. In this particular case, we're given BCC from the previous slide. I know that I have this relationship between my axial length and the radius. So last thing I'm going to do is I'm going to use this formula and I'm going to plug in the radius and I'm going to end up with this number, exceptionally small, right? And I want you to think about it. That's actually the distance between the two adjacent atoms, right? That's going to be this distance either right here or here or here, and all of those are the same, right? Because I'm looking at the body-centered cubic structure. All right, so what happens if we're, oh, no, not yet. I was about to jump into the face-centered cubic structure. Not yet. I would like us to also look at the atomic packing factor. This is going to be really important, especially later in the course. We do want to know how much of space is actually occupied by atoms and how much of space is empty space, okay? And this is how we define the atomic packing factor. So APF. Now, once again, atomic packing factor, we usually measure it in percentage. And if you look at the equation, it says that it's a volume of atoms, right? So it's the volume that is occupied by atoms divided by the entire available volume, right? And that's how we say it, atomic packing factor, right? Now, for a BCC, why don't we find it without looking at the answer, right? Why don't we apply our own knowledge and find out what the answer should be? For a BCC, it's going to be what? Volume of atoms in unit cell. You are looking at the BCC cell right there at the bottom, and we already know that we have 2 atoms, right? Or perhaps I should say 2 equivalent, right? Because one atom is a whole and another one is chopped into 8 pieces, okay? Now, assuming those are spheres, right? To find the volume, I'm going to use the volume of a sphere, which is going to be 4 over 3 pi r cube, right? That's just the volume of a sphere. Divide by, now I see right away, I have this problem here as well, so I'm trying to correct it. Um, Divide by the volume of the cube, which is a cube, but I want to use a radius because that way I'm going to use this because that way I will be able to start canceling things out, right? And so that would be 4 to the power of 3, that's 64, right? 64 r cube divided by 3 times square root of 3, right? Now, I can probably cancel certain things out. I'll try to keep canceling things out till I can not do that anymore. Now, this cancels out, this cancels out. This is your, here I will have just 8, right? So that means I will have what I have left over, pi, which is my 3.14, right? And then I multiply it, and I'm going to flip it, square root of 3 divided by 8. Pretty sure that's what it is. And then if you ought to do the math, I'm going to approximate it. You will find out that the answer is 68%. Okay. So what that means is that 68% is occupied, perhaps 68% of space is occupied by atoms, okay? Meaning that the rest empty space, right? Okay, so hopefully that makes sense. And later on, you'll find out that we do need to know there's a difference between a densely packed material versus not a very dense, right? But both BCC and FCC are considered to be densely packed materials. All right, showing the answer here as well, step by step, in case if you would like to review it. Now let's jump to face-centered cubic structure. It's going to be a lot easier because now we know the concept, what we're trying to define, what we're trying to calculate, and how we're doing it, right? So now we're looking at the FCC, right, which is a face-centered. And right away, I'm going to jump into this structure. Since this is a cubic, the first 2 points will remain the same, and specifically that the axial lengths are equal. A is equal to B is equal to C. The angles are identical, just as we looked at the BCC, right? Alpha is equal to beta, and it's equal to gamma, and it's 90 degrees. Now, the next says 4 atoms. And again, I don't want you to memorize it, because if we have to memorize something that just we lose the knowledge that we just store in the memory. I want you to try to understand why 4 atoms. Okay, so now I'm looking at the bottom sketch right here, and I already know that I have 8 pieces of 1/8, right? So I'm gonna have just to make sure that I am not inventing anything, right? So that's going to be 8 times 1/8, and I'm talking about these guys right there, right? There's one in the back, we can't see it, right? So it's all of these. And now, instead of one hole in the middle, one whole atom, you actually have a slice of each in the face, right? So that means I have this 1, 2, 3, 4, 5, 6. Okay, so that means I have 6 times 1/2. Now, hopefully you can visualize it, right? Because some of those we see, they are right in front of us, but you guys can imagine that you have this half in every single face, right? And you have 6 faces, right? With that being said, you have 1 plus 3, and that gives you 4 atoms, okay? Now, coordination number is 12. Again, very easy to track. Just choose one of the atoms and then see how many neighbors it has, and you will find out that it has 12 neighbors. Example of FCC metals include aluminum, copper, nickel, gold. Okay. All right. So now let's establish a connection. I see the same mistake as well. The square root shall not extend beyond the number. Okay, my apologies for having a mistake. Let's see if you guys can actually derive this relationship on your own, okay? But it's probably going to be a little bit easier here, right? So we're still looking at this side, which is going to be your 4 times a radius, right? Because this is your radius, this is 2 radius, this is radius, sum it all up. That's how you end up with 4 radius. And now if I am to look at this triangle, right? This is my A, this is my A. So I know that my A squared plus A squared is equal to 2A squared, and the square root of 2A is going to be equal to 4 radius. Okay? If that is too fast, just pause the video and review it on your own. All right. We have a problem that we will now attempt to solve on our own. Okay. So we are asked to estimate the axial length A for FCC aluminum with an atomic radius, and here's your atomic radius, okay? Well, I already know using this relationship that my A is equal to 4 radius divided by the square root of 2. Now, all I have to do is to plug in this number, which is going to be 4 times 0.143 divided by the square root of 2. And it looks like the answer is going to be 0.405, and I think I have it on the next slide. Okay, relatively simple. I believe in the homework I'm giving you something that is a bit more challenging, right? So you guys can step up and develop skills, right? Because these questions are very, very introductory. Now, why don't we also estimate the atomic packing factor for an FCC? And right away, before we even look for the number, I want you to envision what we've seen before versus what we see now and think, okay, which one is actually denser, right? Where do I have less free space? Perhaps in this one, right? You can kind of like predict that just by looking at the picture, but let's see if this is the truth, right? So the APF, the atomic packing factor for the FCC is going to be volume of atoms. Keep in mind this time I have 4, right? So it's going to be 4 times volume of the sphere divided by the unit cell, which is going to be divided by A cube. And keep in mind is your A is right in here. It's 4 radius divided by the square root of 2. So it's going to be uh, mhm. 4 radius, I'll put it right here, 4 radius over 2, and all this to the power of 3, right? It's going to be 64 r cubed divided by 2 square root of 2, right? Now let's see if we can cancel things out as much as possible. Right, I'm going to pull up my calculator. And first I'm going to get rid of some apparent things, right? Uh, now, so let's divide 4 times 4 is 16, and divide 64 by 16, there's going to be 4, okay? Now I'm going to divide 4 by 2. That's going to leave me with 2. Okay, let's hope that I did not mess it up. Now, what is left is pi, which is 3.14 divided by 3 times, and keep in mind I'm going to flip it. It's going to be square root of 2 divided by 2. Yeah, that looks good. And if you are to estimate the number, you will find out that the answer is 74%. And if you do remember that earlier, we found that for the BCC, the atomic packing factor was 68%, meaning that 74% is occupied by the atoms, right? Those 4 atoms. And then the rest, 26%, is the empty space. This is something that you do want to remember, and especially for the quiz or the exam, you may encounter a problem where you would need to know this knowledge, right? Um, you also you also won't have to memorize it because you can always start with a sketch, right? As long as you can draw this, you can easily find out all of those equations and connections because it is relatively simple, okay? Now, what is the conclusion? Is that the FCC metals are more efficiently packed than BCC metals. Later on, you'll also find out that they're softer than BCC because they're more efficiently packed, right? Or densely packed. Okay, now I am including 3 slides for hexagonal close packed. Once again, the reason I'm including it is because most metals, they crystallize in either BCC, FCC, and HCP. But at this point, I think it will be redundant to go over another crystal structure. I will allow you to look at these 3 slides on your own. And all of this information is very, very similar. Perhaps one thing I will just say is that hexagonal close-packed structure, HCP, has the same atomic packing factor as the FCC, the face-centered. And examples include cadmium, zinc, titanium, and magnesium. Now, we often also need to know the atom positions, okay? And it is relatively simple. The way you can think about it when we encounter the atom positions is these are coordinates, right? So, and that means that for our crystallographic system, we need our axis, right? We need X, Y, and Z. Now, in a cubic unit cell, the crystallographic system, and you will encounter this in the homework, make sure you don't flip those because it's not up to you to decide what is Z, what is X, what is Y. There's actually, it's predetermined and there is a specific rule we use. And that rule says that the X always comes out of the paper, right? So if this is going to be my origin, right, 0, 0, 0, this is going to be my X. Now, Y is always directed to the right, right? So that means that the negative direction is going to be the other side. And the Z is always directed upward, okay? And so the atom positions are basically just the unit distances along the axis, right? And so if I am, I don't know, let's identify which one. Perhaps let's look at this one, right? So, and you guys will see that your Z is 1, your Y is 1, and the X is 0, and that's why you end up with 0, 1, 1. We use the square brackets, we separate by commas, X, Y, Z. Let me change the color, practice a little bit with this one. Okay, so this one's going to be a bit more challenging because your Y is 1, your Z is 1, and your X is 1, 2, and that's how you end up with 1, 1, 1, right? So once again, atom positions are just distances away from the origin, right? Now, why we need to why we need to be familiar with this, because everything else kind of like depends on your ability to define the atom positions. Because often we need to define the direction in a cubic unit cell. And it is relatively simple. So whenever we need to determine the direction indices, right, we just need to identify the position coordinates of the unit cell where, and now this is important, the direction vector emerges from the cell surface, okay? So let's say if this is my origin and I have this vector. So for me to define this vector, it's going to be very, very simple. I just need to determine the position coordinates where the vector emerges from the cell, right? And I already know that this is actually 1, 1, 1, right? I just defined it earlier, and that means that the vector is going to be, we always use square brackets. We don't use any commas, nothing. We just list it like this, right? And here's an example of this guy right here is going to be 1, 1, 0, right? Again, it's just the coordinates where the direction vector emerges from the cell. And then in here, it's going to be what? 1, 0, 0, right? Again, if that was too fast, pause the video and try to define it on your own so it kind of like makes sense before I move on to the next example. Sometimes you may have to flip the origin, right? And I will actually show you an example right here. This was your origin, right? This was our 0, 0, 0 in prior examples. But all of a sudden, I'm looking at the origin, which is 1 bar, 1 bar, and 0. Whenever we see the bar above the value, that means it's negative, right? So I need to find the value. Keep in mind, this is x, y, and z, where my x and y are negative. And the easiest way to represent that, and you guys will encounter it in the homework. Actually, I should stay a bit longer on this slide. You will encounter something like this in your homework, and a lot of students, what they do is that they keep this as a 0, and then x is negative and y is negative, right? And so they're just going to send the vector right there, and they submit this as the answer, and then they lose the points. And the reason you would be losing the points is very simple, because your vector has to stay within the unit cell. Okay, some students move the unit cell to the other side to make it work. The easiest way to solve this problem is to actually shift your origin. Now envision that this is my origin, 0, 0, 0, right? And perhaps to make it, to make sure that you guys, why don't I, oops, my apologies. Why don't I change the color and I explain what I mean by shifting the origin. This is going to be my new origin. And that means that this is going to be my positive z, this is going to be my plus x, this is my negative x, this is my plus y, and this is my negative y, right? And so -1 for y is going to be this number right here. Negative x is here, right? So I connect this, and that's how I end up with this vector, right? So hopefully now it makes sense. So when you solve the homework, I do not recall which exact problems I've chosen for this year, but I am pretty sure that there will be problems as well as in your exam where the question, when you encounter the question, it seems very challenging till you figure out where you want to place the origin. Because once you move this origin around, you're like, oh, that's actually very, very simple. But regardless, something that you have to keep in mind, and the instructions in your homework will say that the direction must be within the cell boundaries. So once again, you can't submit something like this. Okay, and I include this entire sketch because your direction vector is not within the boundaries, right? You always need to make sure that it is within the boundaries, and the easiest way to keep it within the boundaries is to actually shift the origin. Usually shifting the origin is very straightforward. Sometimes you have to play around and see which origin works the best. Now, what is the general procedure to actually determine direction indices, right? Well, first you need to produce a direction vector, right? Till it actually emerges from the surface of the cubic cell, right? Now you need to determine the coordinates of point of emergence and origin, right? So entrance and exit. And keep in mind, this is going to be important, that's why I'm going to highlight it. You need to subtract the emergence from the origin, right? Or it's always exit minus entrance. And in all of the previous examples, everything was very, very easy because the entrance was always the origin. It was a 0. So you always had the exit was the answer, right? The coordinates of the emergence was the answer because it always started in the origin. Later on, I'll show you example where your direction vector may start not in the origin. So there you'll have to do a little bit more of math. Now, once you do the math, you also have to ask yourself, well, are all uh, all the numbers are the integers. If they're yes, you're done with the answer. One thing to keep in mind is that you do need to convert it to make sure that you use square brackets. And if the number is negative, you need to put a bar above the number. But if the numbers are not all integers, you need to convert them to the smallest possible by multiplying by the integer, right? Let's look at the example right here. So you have this vector right here, right? It starts at 0, 0, 0, and it emerges at 1, 1/2, and 1. So to define, right, to find the direction indices, right, or to define this vector, we need to do exit minus entrance, right? And that's how we end up with 1, and I'm going to actually write down it right here. I want you to follow my thought. 1, 1/2, and 1, right? That is what I found. Next question is right here. Ooh, I may need to pause for a second to find a charger. I'm now in here, and the question is, are all numbers integers? And no, one of my numbers is actually a fraction. So what I need to do is that I need to multiply it by 2, right? And I end up with 2, 1, and 2. Now everything, all numbers are integers, so I can put the square brackets, and that is going to be my answer. To allow you practice a little bit more, I'm giving you another example problem here. Pause the video and go over it if you feel like you would benefit from more practice. Because in this particular example, you guys will notice that even though the origin is here, but the vector doesn't come out of the origin. But you will easily notice that the concept remains the same, nothing new. The only thing here is that when you end up with a negative value, you make sure that you convert the minus sign as the bar above the integer. Now, the last thing that we would cover today is a few more Miller indices, right? So sometimes you need to identify the crystal planes, okay? And you're looking at the example of such plane. Instead of direction, we need to identify the planes. And to identify those, we're using the Miller indices. Now, what we need to keep in mind is that the indices, the Miller indices, are reciprocals, and that's the key word here. Never forget about that part. Often during the exam, students understand what they're supposed to do, but they forget the reciprocal part. So the indices are reciprocals of the fractional intercepts. Okay, so once I have my plane, right? If you guys look at this plane right here, right, that is highlighted by green, I need to identify the intercepts. And the intercepts are actually very easy here for x, y, and z, and I'm going to keep it like this. The intercepts are 1, 1, and 1, right? That's very, very easy. The next step, you guys already see that the answer is 1, 1, 1. But this is not enough. Then you need to take the reciprocal of those intercepts. And for this particular case, it happens to be the same. This is why the next step is going to be, we use square brackets, no commas for planes. Okay, and so the answer is 1, 1, 1. And those are not X, Y, Z anymore. Those are H, K, and L. Okay, I'll have a slide that will go over that point too. Now, just to summarize the procedure, I just described it with an example, but let's look at it one more time. So, first thing you need to do, you need to make sure that the plane doesn't pass through the origin. Well, if your plane passes through the origin, then you won't be able to find the intercepts, right? So you always need to make sure that the plane doesn't go through the origin, okay? Now, first step is you need to determine the x, y, and z intercepts, right? That's where your plane chops the axis, right? And that's how we find the intercept. Next step, please do not forget about it. Well, during homework, during quiz, and in class, during lectures, the majority of students, they always remember that they need to take the reciprocals. But during the examination, this is where we usually make those unfortunate mistakes, right? Make sure that you find the reciprocals of those. Now, next question is again going to be, are you dealing with fractions? If no, you're ready to jump to the next, right? You're ready to format the answer as with circle brackets. And if the answer is negative, keep in mind that you still need to have a bar above the answer, just as you would do with the direction vectors. Now, and whenever we deal with the final answer, when we're looking at the plane, we use HKL instead of XYZ because there's a little bit of a difference. Keep in mind is that we're going through this reciprocal point. Now, if we end up with fractions, then we need to take one more step, and that is we need to clear fractions, right? And the way you do it is you multiply it by an integer to determine the smallest set of whole numbers, right? This is relatively straightforward. And then you just go back to the same routine. And I believe I have perhaps an example. Okay, we will look at very, very simple examples. Uh, but they will be enough to prepare you to your problems in homeworks and exams. So let's look at this plane, right? This is the plane right here. And the answer is that you already see that your H, K, and L is 1, 0, 0. But we want to understand how did they come up with this, right? How did they come up with 1, 0, 0? Let's start with step number one, right? First, we need to find the x, y, and z, which is the intercept. And you will find out that it intercepts the x at 1, right? And then it runs parallel to either z or y. So you basically have 1, infinity, and infinity, right? Because we use infinity whenever it just runs parallel somewhere in the infinity, they are destined to actually intercept, right? Now, if we are to take the reciprocals, you will have 1, so this is step number 2, you will have 1 divided by 1, which gives you 1. Now you will have 1 divided by the infinity, which will give you 0 and 0. And that's how you end up with HKL equal to 1, 0, and 0. Okay, let's look at this example right here. Even though you already see the answer, 632, but why don't we just understand where all of those things come from, right? Because in the exam, right, you will probably, and let me hide it from you, you won't see this, okay? I'll give you everything else except that final answer, and it will probably be a multiple choice question where you have to choose it, right? So first thing I do, I'm gonna use this little space right here to be able to solve the problem. X, Y, and Z, right? Well, X is 1/3, Y is 2/3, and Z is 1. Next step is take reciprocals, right? Again, it is very, very common mistake when students rush and they start clearing the fractions, right? But before we get there, we need to make sure that we take reciprocals. So reciprocals are going to be 3 over 2, and 1. Now I'm looking at fractions. To clear those fractions, I will have to multiply by 2, meaning I'm left with 6, 3, and 2, right? Square, round brackets, sphere brackets. And then let me uncover it here, and then this is how we came up with this answer. It should be relatively straightforward. It should be relatively easy. However, if you feel like, well, I'm a little bit behind, you just need to pause the video and work at your own pace. Work on your own. Once you are there, things will get a lot easier. And again, during the examination, if I am to provide an answer like a question like that, there are only 2 ways to do that. I will either give you a plane and I would ask you to determine the Miller indices HKL, or something that you would actually a part of your homework where I'm giving you the Miller indices, right? I'm giving you the plane and you have to draw it, right? So here, just more examples in case if you feel that you do need to go over these examples, pause the video and to go over these examples on your own. They're relatively easy. One more thing we need to be familiar with is interplanar spacing, which is relatively simple. What it means is that interplanar spacing is just the distance between parallel closest planes with same Miller indices, right? And that's literally this distance right here. Because how would you understand that? Well, earlier we said that we use this unit cell, right? This simple cell to characterize the material, but the unit cell, it composes a large spaced lattice. So that means that these planes that you identify, right, like the plane right here, it actually occurs over the entire crystal, and there's a specific distance at which it occurs, right? And so this distancing, spacing, the interplanar spacing, and we always specify for which plane we are looking at. That's why we say HKL. It is as easy as A, and A in here is going to be this distance right here, right? It's the unit cell length divided by the square root of h squared plus k squared plus l squared. And the way you find the HKL, it just depends on which plane you're looking at, right? If you're looking at 110, then you're going to plug in here 1 squared plus 1 squared plus 0 squared, right? We will look at the example like that as well. Now, before we conclude this lecture, one thing I'm going to tell you is that so far, I do not want you to get the impression that all materials possess specific crystal structure. It is true for the majority of the metals. However, some of the materials are very unique, and iron happens to be one of those where they, depending on the pressure and the temperature, they can exist in different crystal structures. And we call this phenomenon as polymorphism or allotropy for pure elements. So what actually happens, and let's look at iron. Prior, iron was mentioned on multiple slides, and every single time it was mentioned as it has BCC structure. But the unique thing about iron is that iron exists, for the most part, as a BCC. However, at 912 degrees C, if you actually heat it up all the way to 912, the unique thing about iron is that it's going to transition to FCC, and we usually call it gamma iron, right? That's how we distinguish between the two. Now, if you bring it to 1394 degrees C, it goes back to BCC, okay? It goes back to BCC. But we do want to distinguish between those two, the original BCC and the BCC between these high temperatures. And this is why this iron structure we call an alpha iron, and this one is a theta iron, okay? Um, Not a theta, but I will not be able to. Okay, I'm not gonna waste your time, guys. I forgot how, I'm not sure I'm using the proper Latin name for this letter. But you guys get the point. Now, once you cross the 1539 degrees C temperature, then you are actually liquefying iron. So once again, I do want you to be familiar with that typically every material has a specific structure it exists at, right? However, some of the materials are very unique, meaning that depending on the temperature or the pressure, they can actually change their crystal structure. Okay, and we call this phenomenon either allotropy or polymorphism. Um, Now, I could have shown it earlier, but I left it as the final slide, is that I did want you to see what the amorphous materials look like, right? So basically they are random, right? The position of atoms is very, very random. An example of those include polymers, glasses, and also some metals. Um, Usually it happens to a metal if you liquefy it and then if you cool it, we will actually look more into this specific point, is that when you cool the metal, and if you cool it too rapid, right, too fast, the atoms Think about it as they're not given enough space to walk back to the position where they are supposed to be. And that's how you can end up with something that looks disordered, right? But I do want you to keep in mind is that amorphous materials, they are usually disordered, right? Random, possess no order in there. Now, polymers can be semi-crystalline, and the semi-crystalline materials are the ones that are amorphous in general, but they may possess these regions that do have crystallinity.